Welcome back, students. We were discussing operational amplifiers and especially ideal operational amplifier with its characteristics. Two more characteristics define the ideal operational amplifier. Number 6 would be infinite common mode rejection ratio. This is an advanced topic, and CMRR we would understand as we go along the lecture. The CMRR noise voltage should come out to be 0 for an ideal operational amplifier. The last characteristic of an ideal operational amplifier is its slew rate. Please see the spelling. It is not a slow rate, it is slew rate. So slew rate for an ideal operational amplifier should be infinite. Slew rate gives us an idea about how fast the output of an op-amp changes when input of the op-amp changes. So now, as we have seen that the op-amp is used for DC signals as well as AC signals, it is kind of an all-round amplifier that way with advantageous properties. So DC has a frequency of 0 Hertz, so it does not matter, but the AC signal can have a frequency right from very low Hertz to about high frequencies like megahertz and gigahertz and nowadays even terahertz. So now this fast changing input sometimes tends to lag the output. The output does not change as fast as the inputs is changing. This happens because we have semiconducting components inside the IC and which physically involve movement of a current in two different directions. At very high frequencies, the electrical fatigue tends to set in and high frequency changes at the output show a lag with input, but not in the case of ideal op-amp because it has infinite slew rate. So we move on with further characteristics of op-amp. The actual op-amp is never ideal, and a practical op-amp never has infinite input impedance and 0 output impedance. Using feedback characteristics, the scientists or the engineers try to make them exhibit characteristics that are point-wise, numerated in ideal case. So on your left is the ideal voltage transfer curve, and as we can see that the moment the voltage is applied, we get to see a standard flat output with respect to the x-axis. When we reverse the voltage, we see a standard flat line with the negative x-axis. But this change here from 0 to a certain high value is instantaneous in the case of ideal op-amp, but it is not instantaneous as far as practical op-amp is concerned. On your right, one can see the practical non-inverting voltage transfer curve, and it is interesting to note that input voltage and output voltage are on the same quadrant. So as you can see, the changes from 0 to certain high value that one gets from the output of the op-amp is at around 45 degrees, whereas it was instantaneous in the case of ideal op-amp. Likewise, we get to see the changes in the first and the third quadrants for non-inverting voltage transfer from input to output, but the change is not instantaneous. The figure here shows, of course, the output of the practical inverting voltage transfer curve. So, as you can see that as the voltage increases along the positive direction of x-axis, the voltage that is obtained is in the second quadrant, that is negative. Likewise, we also have, as the voltage increases in the negative direction, we get the output in the fourth quadrant, that is again out of phase. So, input and output are out of phase in this diagram. So, open loop configuration. So, open loop configuration, wherein we do not have any feedback from the output to the input, is characterized by certain characteristics. We have that open loop indicates that no connection should exist between the output and input terminals in whatever manner. Output signal would not be fed back in any form to the input signal. So, in this case, the op-amp simply behaves as a very high gain amplifier. Typically, for 741, we have the gain of around 2 into 10 to the power 5, that is around 2 lakh. Now, this higher gain is actually used, as we will see later, for switching, because the op-amp would function in only two states, that is either plus saturation or minus saturation. It would be very difficult for the op-amp to give a stable output in this configuration. So, open loop configuration is used in three different manners, that is, the op-amp is used as a differential amplifier, number 2 as inverting amplifier, and number 3 as non-inverting amplifier. In the first case, it is a differential amplifier. As the name suggests, it is the configuration wherein voltage is fed to both pin number 2 and pin number 3, and depending on the magnitude of voltage at pin number 3 and pin number 2, the output would either be in phase or out of phase. So, differential amplifier is the VD input, which is the difference between V1 and V2 as shown in the circuit diagrams in the previous slides. Number 2, inverting amplifier. Inverting amplifier is a direct offshoot. Both inverting and non-inverting amplifiers are direct offshoot of differential amplifier. In inverting amplifier configuration, we provide the input voltage, whether AC or DC, to pin number 2 only. We ground the pin number 3. That way, whatever voltage, magnitude of whatever voltage is applied to the pin number 2, it is amplified. So, again, since pin number 2 is only working, therefore, the output at pin number 6 would be out of phase with pin number 2 by 180 degrees. Pin number 3, non-inverting amplifier, is the amplifier that we obtain whence we ground pin number 2 and we provide the input voltage to pin number 3. In this case, it is important to note that pin number 6 will give an amplified version of the voltage that is input at pin number 3, and both output and input would be in phase. So, moving on, we will see how the differential amplifier is configured. As one can see from the figure that we have the input voltages at both pin number 1 and pin number 2 and pin number 3. In this case, we always affix a resistance typically of the order of 330 ohms to about 1 kilo ohm with pin number 2 and pin number 3, just to provide stability to the circuit. The output at pin number 6 would be 2 into 10 to the power 5 times Vd, this being the open loop configuration. So one can understand that the amount of voltage that you get at pin number 6 is expected to be very high, but that is not so, as we'll see in the next couple of slides. The inverting amplifier is shown in this case, and one can see that the minus terminal, that is pin number 2, has a voltage source connected to it via a resistance, and pin number 3 is grounded. Hence, pin number's output voltage at pin number 6 would be out of phase with the input voltage at pin number 2, and pin number 6 would be the voltage at pin number 6 would be amplified version of the voltage that is input at pin number 2. The non-inverting configuration is shown in this circuit, and in herein we note that pin number 2 is grounded and pin number 3 has a voltage source having a resistance in series with it. So all this configuration thing happens only after the 741 IC is energized using a dual power supply. Right. So moving on, the need for a feedback. The need for a feedback in an operational amplifier occurs or is required because of the very high gain associated with it. Now, it is important to note that, like in this figure, we have the power supply of plus minus 15 volts, and in open loop configuration, whether differential, whether inverting or whether non-inverting, whatever voltage we have at the input, that is going to be amplified by 2 lakh times, that is around 2 into 10 to the power 5. So hence, even with an input of 1 millivolt, the output theoretically should be 1 millivolt into 2 to the 10 to the power 5, that is 200 volts. Again, this looks like as if it comes from a fairy tale, and in ideal case, theoretically it might be possible, but in practical case this is not possible. That's because the op-amp is powered by a dual power supply of plus minus 15 volts. So effectively, the difference between the 2 points, that is pin number 7 and pin number 4, is 30 volts. 15 minus of minus 15 is 30 volts. So anything of the order of 30 volts, bigger than 30 volts, would make the op-amp go into a plus saturation or a minus saturation. So as we understand from output characteristics of any amplifier, that there are 3 regions wherein an amplifier is biased. Number 1 is the saturation region, number 2 the cutoff region, and number 3 is the active region. When the amplifier is biased at the active region, only then does it amplify. However, between the saturation region and cutoff region, if the amplifier works only at these 2 regions, saturation and cutoff, then the amplifier can work as a switch. That is, saturation means maximum amount of current flows through the circuit, and at cutoff, 0 current flows through the circuit. So the same amplifier can be configured. In this case, the op-amp can be configured to behave in a digital manner or an analog component. When the op-amp is configured in open loop configuration, then it works at plus saturation and minus saturation, and hence that is it works at saturation and cutoff, and therefore this op amp behaves as a switch. In the active region, when, as we'll see later on, in the active region the op amp behaves like an amplifier, but for that there is a requirement of a feedback. So hence feedback is very important in an op amp so that it behaves as an amplifier and offers a stable response. A feedback amplifier in the op amp is called closed loop amplifier, and the feedback forms a closed loop between the input and the output. Hence, in a closed loop amplifier we have two blocks. One is known as the feedback circuit and other is the op amp, and which are connected together. Feedback in an operational amplifier can be of four types. Number one, the voltage series feedback, wherein voltage is fed back to the input in series. We have voltage shunt feedback, wherein the voltage is fed back to the input in a parallel fashion. Number three is a current series feedback, where the current is fed back to the input in series. And finally, the fourth configuration, current shunt feedback, wherein the current is fed back to the input in parallel. So, as a diagram, the four configurations are shown here. Top left is the voltage series feedback. Herein, there are two portions of each diagram. On the left is the input portion and on the right is the output portion. So, output of the op amp is actually the input of the feedback circuit, and output of the feedback circuit is now the new input of the op amp. So, as you can see, in all the configurations we have the cyclic manner in which the signal is processed. So, voltage series feedback, as we can see, voltage is always measured in parallel. Hence, for both voltage series feedback and voltage shunt feedback, the input of the feedback circuit or op amp output is always tapped in parallel. So, herein we have on the right portion of the top two figures, we have the output of the op amp in parallel being tapped and fed to the feedback circuit. The output of the feedback circuit, which acts as the input of the op amp, is shown in two manners. On the left top figure, we have the series feedback, and top right figure we have the shunt feedback of the voltage. Shunt, as we see, is parallel and series is series, where A is connected to A and B is connected to B directly. The bottom two figures identify with the current, and again it is interesting to note that on the right portion of the circuits, that is output of the op amp and input of the feedback circuit, the current is always measured in series. On the top two figures with voltage, we see that voltage is always measured in parallel. Output of op amp is in parallel, whereas output of the op amp is in series in the case of the currents. In this way, we can see that the bottom two circuits identify with the current series feedback on the left and current shunt feedback on the right. So, these are the four configurations which are available for the op-amp to give a stable circuit. So, voltage shunt and voltage series are the most commonly used configurations in the case of an op-amp, and by using a feedback circuit we feedback a part of the output signal to the input circuit, not whole of the output, never a whole, the entire output signal is never fed back to the input, only a part of the output signal is fed back to the input circuit. So, again feedback is of two types, positive feedback and negative feedback. So, in positive feedback the input of the feedback circuit and output of the feedback circuit are configured in such a way so that the output of the feedback circuit and input of the op-amp are in phase, that is 360° out of phase or 0° in phase. That simply means that output of the feedback circuit actually strengthens the input of the op-amp. Now, this kind of a feedback is used only in the case of oscillators. That's because it has to be regenerative in nature. Otherwise, for all practical purposes, the feedback that is given to an amplifier is always negative in nature, which actually reduces the voltage gain, but it imparts stability. In this case, we will use for an op-amp, we will use the negative feedback. The disadvantage of positive feedback is that if there is a noise in the output of the op-amp, then it gets multiplied manifold when we have a positive feedback. Now, taking out parasitic signals is very important, else the signal to noise ratio of an amplifier would be very low and the amplifier would not be of any practical use. So, the summary is that the negative feedback is of utmost importance in any amplifier. Negative feedback imparts stability to the operational amplifier. So, for all practical purposes, as we study op-amp in detail, we would be using number 1, closed loop configuration, and number 2, negative feedback with the closed loop configuration. So, negative feedback is preferably used in op-amp circuits since a very small differential input is necessary to create a large signal at the output. And if we provide a positive feedback, then saturation of the op-amp would occur, thereby burning up the operational amplifier. Any circuit component cannot work at saturation for long periods of time. So, in the lectures that are upcoming, we would be discussing how closed loop configuration is better than open loop configuration for the op-amp. So, what are the things that we would be looking for in a closed loop configuration and comparing it to open loop configuration of the op-amp? First, we will go back to the ideal characteristics. Number 1, what should an amplifier possess? That is, it should have very high voltage gain. Number 2, it should have a very high input impedance. Number 3, it should have a very low input impedance. And number 4, it should have a very large bandwidth. Hence, the points to ponder upon and consider in this case would be whether by using closed loop configuration, whether we are increasing the input impedance compared to open loop configuration, whether the closed loop configured op-amp exhibits a smaller output resistance compared to open loop configuration, and finally, whether the bandwidth associated with closed loop configuration actually increases when compared to the bandwidth obtained with open loop configuration. So, the voltage series amplifier circuit is what we are going to consider, and from the figure we understand that the feedback provided, as we can see, is to the pin number 2. So, we stop here today. Thank you so much for attending this lecture, and looking forward to the next lecture where we'll discuss the details. Thank you so much.